طيب بسم الله الرحمن الرحيم. So last time we started to talk about the matrix to evaluate the best routes as part of the dynamic routing protocols, and we talked about the offline matrix versus the real-time matrix. We also talked about the criteria based on which we can evaluate the performance of the dynamic routing protocol, including the time to conversions, including scalability, including the simplicity of the implementation and the low resource requirements. And we discussed in brief these criteria applied on the distant vector routing protocols. And we said that distant vector routing protocols, because of the fact that they maintain partial view, they don't maintain global view, then the algorithm runs on a small set of route entries. So in terms of implementation, it's simpler. In terms of resource requirements, it's lower compared to link state, of course, where link state they require so much storage and computation because of the fact that the link state dynamic routing protocols they maintain global view where they store the link state database. But in terms of slow conversions, distant vector routing protocols they tend to be very slow because of the fact that they have to incrementally exchange the route updates and they do not maintain any global view. So the conversions is actually very tricky to be attained, and therefore route updates for distant vector routing protocols they tend to be periodic. And also in terms of scalability, if the network grows very large, the time to conversions and the exchange of the updates will be very, very expensive. And in that case, the scalability is affected. Also, routing loops, they happen again for distant vector routing protocols because of the fact that distant vector routing protocols, they maintain partial view. They do not maintain global view, so they don't know when they forward the packet that these packets will not go into loops. And today, inshallah, we'll cover this routing loops in details. So for the different phases for dynamic routing protocols, the first phase is what we call the cold start. So for cold start, the each router will individually and independently get or collect information about the directly connected routes. The directly connected routes, they get detected automatically once the interface is activated or started. And as we said, this happens through the physical layer. So automatically, once the interface starts, this link will be detected, and this link will be detected, and the entries will be put in the routing table, of course, with a metric of 0 to indicate that these are directly connected. This cold start step is totally agnostic to whatever dynamic routing protocol we're talking about. So regardless of whether it's link state, it's a distant vector, it doesn't really affect this cold start phase, and this happens before I even start any routing protocol. So same thing happens for router 2 and router 3. All of them, they will independently collect information about the directly connected routes, and they will put it in the routing table. Okay. Then the network designer or the network analyst may choose to select the static routing, in which case he or she will have to insert routes in the routing table manually, or the network designer will start one of the dynamic routing protocols like REP, OSPF, EIGRP, and so on. Okay, so in the next phase, once I start the dynamic routing protocol, assuming that I have started one of the dynamic routing protocols, in that phase, we start to exchange routing information. Okay, and here, this particular example talks about the use of RIP, because how did I know this? Because of the fact that the metric is actually is the number of hops. So here, router 2 will get or receive information from router 1 and router 3. Router 1 will receive information from router 2, and as well router 3 will receive information from router 2. Okay, so since we're talking about the metric as the number of hops, then router 2 will learn about network 10.4.0.0 from router 3, and in that case router 2 will put it here. Okay, router 2 will also learn about the network 10.1.0.0 from router 1, and again it puts it here, right? And of course router 3 will send information about 10.3.0.0.router 2 to router 2, which will ignore it because this entry is already in the routing table. So some of these entries it will be ignored, but the route about this network and this network, it will be inserted to the routing table of router 2. Similarly, router 1 will learn about the network 10.3.0.0 from router 2, and then it will put it here. Once it puts it in the routing table, it increments the metric. So if the metric is 0 here, so it will increment it to be 1. Okay, and similarly, router 3 will learn about 10.2.0.0 from router 2, and it will insert this in the routing table to and set the metric to 1. So the question is now, is this a steady state or is this a conversion state or not? Does anyone know? Is this a conversion state or not, and why? Anyone can guess? Azam, do you know? Azam, you know the answer? It is the conversion state. Actually, no, it's not a conversion state. ليه بقى؟ عشان because the router 1, it knows about 10.3.0.0, but still it did not learn the this route yet, because this route is 2 hops away. Okay, similarly, router 3 did not learn about this 10.1.0.0 yet because it's 2 hops away. Okay, so this is not the conversion state yet. So we need another round of route updates in order to have router 1 learn about 10.4.0.0 and router 3 learn about 10.1.0.0. This is what's going to happen in the second phase. So here, now router 2 will broadcast all of its routing table, all of it. Okay, and in the routing table I had 4 entries. So these 4 entries, they will go to router 3 and router 1, right? And again, the fact that we send all the route entries in the routing table because we don't know which route entry will be of interest to which router. I don't know. So the only way is to send periodically all the routing entries in the routing table, which of course might be expensive a little bit, but that's the only way. So router 2 will send the 4 entries to router 3 and router 1. So router 3, of course, has all the 3 entries except for 10.1.0.0. So 10.1.0.0, it will get inserted here, and of course, because the metric here is 1, it will become 2. Similarly, R1 will receive all the entries. It will find that it has route to all the networks except 10.4.0.0, which is this one, and in that case it will insert it, and since this is 1, it will be 2. So now this seems to us like this is a state of convergence, and in fact it is a state of convergence, but we can see that visually because we have the global information, and we know that the network has only these 3 routers, okay? But it's very difficult for any of these routers to identify that this is a state of convergence. For example, R1 doesn't exactly know that this is a state of convergence because there might be another router here that it doesn't see, because again it maintains partial view. Okay, R3 may برضو have the same thing, R2 may have the same thing, and so on. So it's very difficult for distant vector routing protocols to detect that this is a state of convergence because of the fact that route updates are sent in one hub broadcast, right? So we don't know how large the network is, and we maintain a partial view, so we don't know whether we have reached to a state of convergence or not. And that's why the most of the distant vector routing protocols, they use periodic updates because they don't know when these updates should stop. So that's these are the phases starting from the cold start, and then the initial route updates until we reach to the conversion state, which is very difficult to be detected for the case of distant vector routing protocols. Convergence must be reached, however, before the network is declared to be operational. بمعنى if the conversion state is not maintained or is not achieved, anything could happen in the network, because before the conversion state is achieved, the routing tables are in an inconsistent state, which means that anything could happen. Packet drops might happen, routing loops might happen, okay? So anything could happen. So, but again, the time to conversions is very tricky, and we don't know how to estimate this time to convergence because it's function of many factors. One of them is actually how large your network is. We don't know how large the network is, and since in distant vector routing protocols we maintain partial view, so we have to learn that throughout the time, and we don't know how much time. So you can potentially spend minutes and tens of minutes for distant vector routing protocols to reach the convergence, and even routers, they would not know that, right? So there are two major factors based on which the time to convergence is actually affected. One of them is how often and how fast these routers, they exchange the route updates or routing information. So the more often and the faster they exchange route updates, the faster they will reach the conversions. However, there's a big trade-off here, because remember that every time you send route updates, you have to collect all the entries in the routing tables, which might be like few megabytes. So I cannot send like every 1 second. I cannot send 1 megabytes. I cannot afford sending this huge amount of information every second from every single router in the network, right? So we have to have a trade-off. And in fact, RIP in fact uses 30 seconds, okay, as a time interval to send route updates, which might sound significant, but it's practical because of the fact that every 30 seconds you send all the entries in your routing table. That's pretty expensive. Okay. Number two is the speed of calculating the routes. And that the speed of calculating the routes is dependent on the algorithm and how simple the algorithm is. Okay. So for distant vector routing protocols, the time or the speed of calculating the routes might be low, which is good. But the speed of broadcasting, the speed of broadcasting routing information is also low. And that's why the time to convergence for distant vector routing protocols is actually very high. It's very, very large time. And that's why distant vector routing protocols are good for reasonable sized networks, not for very large networks. Okay? Yes, the speed, sorry, يعني not the speed, the time of computing best routes. The time for, yes, yeah, this is the time for computing the best routes is actually low. Why? Again, because of the fact that the algorithm runs on a partial view, صح? And the algorithm actually it receives the route updates, and then only it cares about the new ones. So it takes the new one, and then it tries to find whether it's better than the one in the routing table or not. So every time the algorithm runs on a partial view, صح? But in link state, the algorithm runs once on all the link state table, right? So the time to calculate the best route for link state routing protocol, because it gets run against all the link state table, is significant. But in the case of distant vector routing protocols, the time is short because it runs only on a partial view. Is this clear? No, that's well. No. The speed is high. Okay, so if the speed, then the speed is fast. It's my mistake actually. The speed should be fast, or the time should be lower. Okay. طيب, so اتفضل. طيب. So rep version 1 and rep version 2, okay, of course they use periodic updates, okay, and the time interval, or the time that has to pass before I send all the entries in the routing table is in fact 30 seconds. Okay? So every 30 seconds I have to collect all the information in the routing table and send it. And in many cases I have to send the routing table in multiple messages, not just one message. Because of course, as you can imagine, if the routing table is relatively large, I cannot send just one packet that will have like few megabytes. So in that case, I have to fragment the packet into smaller pieces. Okay. So rep version 1 and version 2, they use periodic updates every 30 seconds. Does that mean that all distant routing protocols, they use periodic updates? No. In fact, very interestingly, even though EIGRP, or Enhanced Inter-Gateway Routing Protocol, it's a distant vector routing protocol. Okay. But unlike all the distant vector routing protocols, EIGRP uses bounded updates. By bounded update, I mean that it's not sent as broadcast to all the neighbors. No. It sends partial updates to bounded number of neighbors, okay? And it's triggered, which means it's not periodic. Okay, so it's non-periodic, and I send only partial updates to bounded number of neighbors. And what that means is, the way that EIGRP works is that it says, okay, so I start this interface, I find that there is a new route or a new link that has been added. Okay, so I will generate a route update about this route only, about this link only. Okay, so I will collect the information about this route only. Okay, so not all the routing table entries in that case. And then I will send right away. I will not wait for the time interval to pass until I send the route update. No, I will send a trigger. Okay, and I will send it only to the neighbors that are affected by this information. For example, I will send it here and here, but not here. Okay, so I will send it as multicast, not broadcast. So rep uses one hub broadcast to send route updates. Okay, so it collects all the entries in the routing table and it sends one hub broadcast, okay, to all the neighbors. Only one hub. Okay, not flooding, not flooding like link state. Only one hub. Okay, the EIGRP it will send partial updates as multicast, not as broadcast. واضح الفرق؟ And it's triggered, which means that it doesn't have to go through periodic updates. Okay, so that's very important. But in order for EIGRP to do that, because this actually defies the logic of distant vector routing protocols. This defies the logic, because we said that because of the fact that distant vector routing protocols, they maintain partial view, they have to send all the route entries in the routing table to all neighbors, right? EIGRP بقى يعني violates this. Okay, but in order for EIGRP to do this, it needs a lower layer of intelligence to learn about the neighboring routers in order to identify that when a change happens, I know that these neighbors will be interested in this change, but not this neighbor. Okay? So in order for EIGRP to know this, it needs another layer of intelligence, which we will learn when we get to EIGRP. Okay? But for now, you can think of EIGRP as a hybrid routing protocol. It's not يعني link state for sure, because it still uses distance and vector. It still uses distances to destinations and direction. Okay, but unlike all dynamic distant vector routing protocols, EIGRP uses triggered updates, partial updates, bounded updates. ماشي كده؟ طيب. So for EIGRP, what is the condition, or what are the conditions based on which we send this triggered updates and bounded updates? The conditions are easy. The first one is that once the interface state changes, يعني the interface اللي هو ايه, this interface goes up or goes down. Okay, that's a state change. So in which case I have to send triggered, partial, and bounded updates. Okay, or route becomes unreachable. Okay, so so the link between router 2 and router 3, it goes down for some reason. Router 3 sends information to router 2 to tell router 2 whether it's alive or not, and router 2 does not respond for quite some time. So this is an indication that the link between them is down, or it got disconnected. Or number three is the route is placed in the routing table. So if a route, if a new route becomes available, and router 3 now informs router 2 about this new route, if router 2 finds this route as a new route and it decided to put it in the routing table, it also needs to inform all the neighbors about this new route. Okay, so it has to also inform all the neighbors about this new route. So this is the triggered, partial, and bounded updates that EIGRP uses. Okay. Any questions, يا شباب, so far? Right. No. Actually, well, as we said, it's triggered update. It's triggered update. So here we send the information or the route update about this particular new route. We send it to all the neighbors as multicast. Okay, so not this one is triggered. Yes, this one is triggered. And also, if a router decided to insert a new route in the routing table, then it needs to send information about this particular route also to the neighboring nodes, and we keep doing that. So which essentially means your point actually raises an interesting issue here, that this is, in a way, this is flooding. يعني in a way, this seems like flooding information about the new route in the entire network, right? Because it's triggered, so I will keep adding this new route in the routing table, and then I will send it to neighbors, and then neighbors will send it to neighbors. So in a way, when there is a new event in the network, right, it gets, but I don't want to use the word flooding عشان ما يحصلش, so that we don't get confused with the link state. So I don't want to call it flooding, but in a way it is, because you know the new change will get triggered by every single router, and every router will send it to all the other neighbors. Okay? طيب, يعني the question now comes, what is the difference between this and link state now, right? So that's why I said EIGRP is kind of a hybrid routing protocol, because it uses non-periodic updates, partial updates, and triggered updates, right? But it uses distance to destinations and directions. It actually it does not use link state table. Okay, it does not use link state table like link state routing protocols. Okay, it still uses distances and vectors. Routers still maintain partial view. They do not have link state table to maintain a global view. So that's why يعني EIGRP is fuzzy, is somewhere between the link state and the distant vector. Is this clear يا شباب؟ طيب, يعني احنا now بقى we're talking about routing loops, and we mentioned routing loops يعني couple of times. Yes, Daniel. Okay. طيب, routing loops. So this is a very يعني simple example that shows how routing loops might happen, right? And we need to be very, very clear and understand this scenario very well, because this scenario based on which we will try to mitigate all the routing loops later on. So let's imagine that router 3 now feels or detected that this LAN is down, right? So logically, as anyone might think, okay, because of the fact that this LAN is down, so let's just cross this entry from the routing table. So we will remove this entry from the routing table, right? And our job will be done, right? Because this route is not existing anymore. So let's just cross it, and that's it. This is in fact it's a logical thinking. If you think about it, that makes sense. But none of the routing protocols actually does that, because of the fact that distant vector routing protocols, they maintain partial view. This simple action that we did now will cause serious routing loops. And let's see how this happens. Router 3 crossed this entry from the routing table, and after some time, after the time interval, router 2 sends to router 3 the route updates, which in fact includes information about 10.4.0.0. You see that? Okay. So very interestingly now, router 3 will say, oh, okay, now I have a new route to a network that has an address of 10.4.0.0 through router 2. Okay. This is stupid. How can router 3 accept this entry from router 2, and it knows that this was the one that's down? It doesn't know. It doesn't know that, because remember, router 3 maintains partial view. So maybe router 2 has another route to 10.4.0.0 through another part of the network that router 3 does not know about. واضح? So router 3 maintains partial view. How would it know that this was the one that got disconnected? So blindly so based on the logic that we have, router 3, it will insert a route in the routing table here with a matrix of 2, because R2 is telling R3 that the distance to 10.4.0.0 is 1, so which means that from R3 the distance is 2. Okay, so this is a very interesting situation now that will cause routing loops. Why? Because router 3 now it has a packet with a destination address of 10.4.0.1. This address clearly belongs to this network, right? So R3 will say, oh, okay, according to my routing table, I have to send it to router 2 and the distance is 2. R2 will receive this and will say, oh, okay, 10.4.0.1, I have to send it to router 3 and the distance is 1. So router 3 will bounce it to router 2 and then the routing loop will happen. Okay? So remember back, this particular problem that we have, I hope you all follow this scenario because it's very important. So why did this problem happen? And I will put the reasons now, because depending on these reasons, we will try to look or investigate a solution for this problem. Number one, R3 removed the entry of 10.4.0.0 from the routing table, okay, prematurely. Okay. Number two, R2 sent route update to R3 about the network it learned from R3. يعني الكلام ده يعني R2 sent the information about 10.4.0.0, which originally it learned from R3 actually. It sent it to R3. Okay? So that's kind of, you know, it's weird. It's weird. How come I learn a network from R3 and I have to send it back to R3? Okay? So that's the second reason. The third reason, R3 also prematurely accepted or incorrectly يعني accepted route update about 10.0.4.0.0. These are three reasons. First, we crossed the network. Second, we allowed R2 to send route update about 10.4.0.0 to the router that it actually originally learned it from. And router 3 incorrectly accepted that. يعني all three reasons, okay, have grouped together to form this particular problem. So how do we balance? R2 will redistribute information about the failed LAN to the router that it actually originally learned it from. This is incorrect route redistribution. So R2 sent information about the network to the one that it actually learned it from. R3 here incorrectly crossed this route from the routing table, okay, and accepted the a new route about this network from another router. Okay, so that's all. So we need to know what is the cause for this routing loops and what is the effect, what is the implication of this. So the cause is that incorrectly configured static routes, and this is regarding static routing. So for static routing, okay, it may very well happen that the network designer inserts some manual entries in the routing tables, and these manual entries are inconsistent with each other and causes routing loops. But this happens with some human error or some human intervention. But the second reason is that incorrectly configured route redistribution. This is what we said about, this is what we call incorrectly configured route distribution. Number three here is the incorrectly configured discard routes. The fact that reason for routing loops to happen. This is due to incorrect route updates or route redistribution. But of course, even if everything goes well and route updates are all correct and we don't cross the route from the routing table, even if we don't do all these wrong things, routing loops might still happen because of the fact that we have slow conversions, right? And as we said, until we reach the state of conversions, the network may actually not be operational, right? And anything could happen because routing tables inside the routers have not yet reached to a consistent state. So this means that anything could happen, and one of these many things is actually routing loops. So packet drops, routing loops might actually happen. So if the conversion state is not attained, routing loops may still happen. Type. If routing loops actually happen, what is the implication of this? What are the effects, the side effects of routing loops? Side effects of routing loops are enormous. One, excess use of bandwidth, right? Because we are sending now data incorrectly. Remember, these two, by the way, these two talk about the data, and these two talk about route updates, and I will explain this now. So excess use of bandwidth, this happens because of the fact that now packets are routed incorrectly, so they keep being sent inside the network and they utilize significant amount of bandwidth unnecessarily, right? So also the CPU resources may be strained. They are being utilized to send packets incorrectly, so it's as if you are wasting CPU time. So every time a packet comes and I process this packet, I consume some CPU time, and then I route the packet incorrectly, and packet loops might happen, in which case the CPU time is wasted. Type. If the routing loops happen, network convergence is degraded. Why? Because actually, if the data is actually being routed incorrectly, this eventually will affect the routing information. Okay, so if packets are being sent on the length incorrectly, this will in fact affect the core functionality of the routing information, which means that the routing information will get delayed, which will affect the conversions, or the routing information will get dropped, may get lost. The routing information may get lost, in which case also this will affect the conversions, right? So routing loops is in fact expensive and they cause enormous effect on the network. So it's best for us to try to do everything to avoid routing loops from happening. But in fact, remember, routing loops, they happen because of the fact that the routers, they maintain partial view. And because of the fact that they maintain partial view, a router may actually incorrectly cross unreachable route, and by crossing, it may actually accept this route from another router incorrectly and insert this in the routing table. So okay, so if we understand this, then we should try to mitigate. We should try to know how to correct this problem. And to correct this problem, we have three major techniques or three major algorithms that can be used to trigger this. One is what we call count to infinity. Okay, so number one is the count to infinity. So let's say that, okay, so router, the first reason we talked about for this routing loop to happen is the fact that router 3 mistakenly crossed this route from the routing table. Okay, so we will avoid doing that. So instead of crossing this route from the routing table, if this link goes down, instead of doing this, we will keep the route, but I will set the metric to infinity, and just forget about 16 for now. Forget about this 16 for now. Okay? So I will set this route metric to infinity. This essentially has the same thing. Okay? This essentially has the same effect, because if I cross it from the routing table, the packets, they will never use this route. If I set the metric to infinity, this is essentially the same. If I tell you that if you go from your house, you will reach to if you want to go to QU, go to this direction, and you will never reach. Okay, then you will not start, right? If the metric is infinity, this means that if you take this direction, you will never reach to your destination. This essentially means you should not use it, But why did we do this? Okay, in order to avoid removing the route from the routing engine. Type. This is one. Number two, if I exchange the route with a metric 1000, okay, the routes they will have to accept it. Why? Because this is infinity, which means that this is an updated route, and I have to insert it here. Even though the metric is higher, but I have to accept it. At least at the beginning, I have to accept it. So this means that this infinity, it will eventually go here and here, right? So this will be good. However, just remember, I will accept this for the first time. But remember that just the fact that this network is not now connected to R3, it doesn't mean that router 1, مثلا, for example, will not have this 10.4.0.0, right? So I don't know, this link has gone down here, but maybe it appeared somewhere else in the network. Okay, so when I receive the infinity, I will have to accept it once. But what is the implication of this? So router 1 now, okay, before it receives the infinity from here, it sends a periodic update about 10.4.0.0 with a metric of 2. Okay? And then it receives the route from router 2 with an update of infinity. Okay? So this is a very interesting situation now, that router 2 will say, oh, okay, I have here infinity, and R1 is telling me that it has a metric of 2 about network 10.4.0.0. So in that case, R2 will have no reason to reject it, right? So in that case, R2, it will insert the 10.4.0.0 here with a metric of 3. And R1 will in fact insert the 10.4.0.0 with a metric of infinity. This is a very interesting situation now, right? In fact, this router 2, at the time of the periodic update, it will send the route entries to router 3. Router 3 will say, okay, I have infinity for 10.4.0.0, and router 2 is telling me that it's 3, right? So this means I can reach 10.4.0.0 through router 2 with a metric of a 4. Right. Okay. And then router 3 might actually send an update again, and we'll keep doing that, because here there is still infinity, So this route entry, it will bounce back and forth between the routers, okay? And every time it gets incremented, right? Because this route update will also reach router 1, okay? Which in that case will become maybe 7 or 8 or something like this, okay? And we will keep incrementing every time, as long as we still have infinity in one of the routers. So this phenomenon, we call it count to infinity, okay? So the route update will keep incrementing every time and will keep bounce back and forth between the routers, and every time it increments, we call it count to infinity, okay? But so what happens is that rep version 1, okay, it uses that technique because if remember, if this route is infinity, routing loops will not happen, because again, if I tell you that a packet that gets sent to this network with a matrix of infinity, then it becomes unusable خلاص. So but now we have this problem of bouncing the matrix back and forth between the routers. So rep version 1 says, oh, okay, so I cannot actually allow this increment to happen forever. So that's why it sets infinity to 16. Okay? So it says, okay, count to infinity seems to be the simplest mechanism to avoid routing loops. So I will use it, okay? But I will set infinity to 16, which means that any matrix more than 15, it means unreachable. Okay? Which essentially means, by the way, that the maximum number of hops in any rep version 1 network cannot exceed 15. The maximum number of hops. واضحة النقطة دي؟ So anything beyond 15, okay, it becomes 16. 16 for me is infinity, and this means that this route is unreachable. So I should never use it actually for routing. I should never use it, right? So even with this count to infinity issue, if I set the infinity to 16, this means that I need like at maximum 16 bounces until I reach to matrix equal to 16, and this route will become unusable on every single router in the network, and the network will be fine, will be stable, and of course the routing loops will not happen. But the problem here is this is very slow. Okay? This is very slow. The count to infinity solves the problem by setting the unreachable network matrix to infinity, but it's slow, right? Because of this count to infinity issue. واضح يا شباب؟ طيب. So this is the first technique, and it seems to, it's not efficient in terms of speed. The second technique is called hold down timer. Hold down timer works on the same logic. So instead of crossing the route, we will keep it, okay? We will not set this to infinity, but we have a flag here, and we will declare this we will declare this route as unreachable. Okay? Which means it's grayed, it's not crossed, it's not removed. We will set it as unreachable. This is one. So number 1, set flag unreachable. Okay? Number 2, start حاجة اسمها hold down timer. Okay? Number 3, send triggered update. So then we will set this route to unreachable. We will start a hold down timer, okay, and we will send triggered update that this route is now unreachable. Why do we start hold down timer? During the time that this hold down timer is running, the current logic or the following logic يعني, will be executed. So during hold down, the current logic is executed. One, route, this route يعني, not used for routing. So if I get any packet, okay, with an address that belongs to this network, I will not use this route at all. Of course, that makes sense. Number two, okay, do not send this route in periodic updates. Okay, we should never send this route in the periodic updates, and I will tell you why now. I will tell you why just now. Okay, we should never do this. This logic will be executed here, will be executed here, will be executed here. Okay, so when I receive, when R2 receives information about this unreachable route through triggered updates, okay, it should do the same. It will put this route in the routing table, it will start the hold down timer, and it will send triggered updates to everyone. Okay, so logically, this triggered update will reach the entire network through flooding. So triggered updates, it will be sent incrementally to all routers, and during the hold down timer, all routers, they will just wait until this update for this route propagates the entire network, and everybody will be informed about it. Okay. Number three, when timer expires, then and only then remove route. Okay, so the logic here is that during this hold down timer, keep informing others about the fact that this timer is not this route is not reachable through you. Okay, and inform others through triggered updates يعني quickly. Okay, after the hold down timer is elapsed, then it makes sense. خلاص, everybody has been informed. Okay, so everybody when the timer expires, everybody should remove this route from the routing table, and everybody will be happy. So the routing loops will not happen, right? But why number two here? Do not send route updates, in periodic updates. So unreachable routes, they should be included in only triggered updates, not periodic. Why? Because remember, the hold down timer starts here, before here. Okay, so which means that essentially R3, the timer expires first. When the timer expires first, this route will be crossed from the routing table, right? If router 2 decides to include this route in the periodic updates, right, then router 2 will inform R3 that this route exists in R2. Okay, and in that case, router 3 might incorrectly accept it. So in order to avoid this situation, that once a route becomes unreachable, we should never include it in the periodic updates. We should only send it as triggered updates. So number two here is very important. واضح يا شباب? So hold down timer, of course, is much faster to reach the conversions compared to count to infinity. There is no bouncing back and forth. This route is a triggered update that will get sent to everyone very quickly. and everyone should be triggered right away. However, of course, as you can see, the logic is complicated. Count to infinity is very simple. It's very simple. It's just setting the matrix of that route to 16. That's it. Okay, but it's very slow in terms of reaching to conversions. It's very slow. So hold down timers tries to solve this slow performance. However, it has to introduce all this logic, which is fairly complicated. واضح يا شباب? Any questions